was a long lab. Okay, let's get started. Chelsea's going to finish up the protein lecture, and after she finishes up proteins, I'll start fat. Some of you are doing great in participation. Some of you have not participated once. This is the time of the semester when candy is the bride. So +2 and a candy will be thrown at you with every participation. Chelsea's gonna start that.
Yep. Okay. So we're gonna start with a recap. I will warn you guys, I have hearing aids. I'm down one hearing aid, especially for participating, so speak loudly at me so I can hear you. So with that, let's start with, so the two methods we talked about on Monday was Kaldal and Dumas. So first, let's talk about, somebody remind me, why do we analyze protein content?
Labeling.
Okay, Sam? Okay? I'm awful at throwing candy.
Okay, but what's the answer?
We have her stare. Give us another answer. What else? Come up with another one. You got the candy already. You can do it. What?
Health.
Yeah, that would work.
Standards,
Like what type?
like
Can you name a product that would have a protein standard of identity? Yeah, so like whey protein isolate, we would say it would have to have 90% or more protein. What was that? Yeah. What's one thing that has
Cece gets 2. This is her first participation.
Oh! If you want to trade your candy, type in at the end of it. Yeah, so if we're labeling, there again, yep, we have to do it by difference. Good, so other things we would do would be like food quality, which adulteration speaks to that, or in the plant, making sure your quality and your formulations are on point. Other things would be with like bioactivity, so if we're looking at like bioactive peptides or enzymes, the enzymes being proteins. So you can go back and look at that slide where we talked about all of that. What are the 3 reaction steps of Kaldal? Told you guys you'd have to memorize this. I wasn't wrong.
First is digestion, second is neutralization, distillation, and third is tension.
What's the principle behind Dumas?
Without looking at your nose.
Yeah. Yeah.
Combustion of substance.
What was that?
Nitrogen combustion.
Nitrogen combustion is correct.
Almost.
I got in the vicinity. You're not any better at talking.
I'm not. I'm stuck at it.
So just as a reminder, so both Dumas and Kaldal work by measuring nitrogen. So Dumas is nitrogen combustion with a furnace, where Kaldal is nitrogen combustion using concentrated sulfuric acid. So they're both measuring just nitrogen. So that's the beginning. I'm going to come back to comparing and contrasting. But first I want to ask you guys, why might there be different nitrogen conversion factories for different protein sources? We talked about this. Yeah.
The bioavailability of different proteins.
So that's not necessarily the protein conversion factor. That is going to be like your protein digestibility, which you're going to talk about coming up.
Wasn't it to do with aromatic
Keep going.
amino acids?
Is it the aromatic ones or a different type? You're right, it's amino acids. Which type would it be? Yeah. Exactly. I'm passing yours still there too.
Wrong answer doesn't matter.
Nope. Chocolate regardless. Close enough. So yes, so it would be the amino acid side chain composition, and so those are the basic ones that have those extra nitrogens to them. Where the conversion, like I said, you guys will be talking about protein digestibility coming up, which speaks to the differences in bioavailability. But this slide here was the slide before in your notes. But so just kind of to reiterate, going back, comparing, contrasting DUMAS, we talked about the principal difference. Which one involves more instrumentation? Caldel or DUMAS? Which one? So the instrument itself is more complex. Which one do you think is more costly? Caldel or DUMAS? Yeah, it's different types of costs. You're right. So the instrument to buy the Caldel, how much did our new DUMAS cost us?
What was it, Cindy? $30,000.
Where, but then you have the Caldel unit, the acid. There is a lot of consumables in parts that you're going to see with the legal, but what's nice about it, what can we say about time, do you think? And this is where you might be saving on cost between Caldel and DUMAS. Which one do you think is faster? It is, because the throughput. It takes us only about, right now we can measure a sample in about 2.5 to 3 minutes a piece. Which, Caldel, we also can only do a maximum of, what? 24 samples at a time?
But it takes a long time.
DUMAS, Lucy's running it today, and she will probably drop 300 samples today, 200, doing solubility. So those are just things to consider. And what's important here, guys, when it comes to exams and other things, the idea is if you were at a company, could you do this? If your boss said, we have money, we need to measure protein, what are we going to buy? Can you walk through and pick and explain why, making an argument for what you would buy? Okay, so we're going to go ahead and we're going to talk about some of the more research-based methods. And, well, so this one isn't necessarily research-based, but this is that secondary method that we talked about, looking at IR. So, for example, looking at NIR or mid-IR. And the IR works by measuring absorbance. And so, as you guys talked about in the spectroscopy section, there's the different types of electronic absorption, vibrational energy, things like this. So when we're using our IR methods, it's doing the vibrational energy of the peptide bond, as we talked a little bit about Monday. There again, it's really rapid, which is super nice. So a lot of this is done in line. So like in the processing plants, they'll actually have, your IR, your NIR instrument right in line as your sample's running through. They can do it. Tonya has a project that, like looking at NIR and like cheese for different things for adulteration. Granted, that's not protein, but it's this idea that you can be using this for a lot of different things. But the problem is it requires calibration. So you have to calibrate it. It's a secondary method. So what would you use to calibrate NIR or IR instrument? What was that?
Caldel.
Yeah, Caldel or DUMAS. So you would use one of the primary methods to calibrate. Yeah. I have to come a little closer. Sorry, Cindy. No, you're good.
How do you detect adulterants in NIR?
So you could be looking at different peaks, like so for specific wavelengths, you could be looking at different peaks that either A should show up. So let's say, for example, if there's a peak that would be for carbohydrates, and if it showed up in your protein and it shouldn't have any carbohydrates in there. So you could be looking for peaks that should show up or changes in peaks. You could also spike a sample to see those changes. But it goes back to really identifying the molecules. So oftentimes with adulterants, you would have to also confirm it with a primary method, and you would calibrate your instrument then as a secondary method. Okay, so some of the research methods we use. One of the research methods we use is, I'm just going to call it the BCA. method because that's a doozy of a word to pronounce. And how this works is talking about the peptide bonds again, the amino acids that proteins have the ability to reduce. They can act as reducing agents. And so you have a BCA reagent that has cupric ions in it, that the proteins in your sample then reduce to cuprous ions. And under alkaline conditions, this turns it from a green color to a really pretty deep purple color. That purple color then can be measured, the absorbance, at 562 nanometers. And so what is the reducing? What's actually giving this reducing capabilities? It's the presence of both the peptide bonds that we talked about have reducing abilities, and also the presence of, for example, like cysteine as an amino acid, or as in tyrosine or tryptophan. What about cysteine or tyrosine could be reducing? Anybody know? Something with their side chains. Tyrosine has an OH group on its side chain, and cysteine has a sulfhydryl group. So that combination there can then reduce the BCA reagent. And so to do that, we need to build a standard curve, which I'm going to show you in a moment. But why do I use this? So this is what I use to quantify proteins in purified solutions. So for example, if I have a solution and I had to centrifuge, and some of my sample precipitated out, well, some of that might be protein I lost. So now if I'm comparing across samples, some samples that are less soluble are going to have more of a pellet than others. So I have to correct everything back for the amount of protein actually present. And so that's one way I would use this. So like I said, we do a standard curve. So like you guys do with the caffeine lab, where what this is down here, this is bovine serum albumin, which is a protein. So we take that protein standard, we dilute it to, in this case, we did about 7 concentrations, and then we measure the absorbance. And so you see how just nice and linear that line is, so then we can compare the absorbance of our samples to this. This is actually one of my old standard curves. So look at that nice little R squared there. Holly has a pretty nice one too, somewhere. So another way we can do it as a research method is the Bradford dye binding method. And this is the one I believe that you will be doing in lab for extra credit. So you'll get a chance to do this. So the principle of this one's slightly different in the fact that instead of using the reducing ability of the protein, it uses its amphoteric nature. Does anybody know what amphoteric means? Can somebody remind me what that term means when we're talking about proteins? Yeah, kind of, sort of.
Does it have a positive and negative?
Yeah, along those lines. So a little bit more specifically.
I was going to say amphipathic. Amphipathic
Oh, yeah.
Is the one for both polar and non-polar.
Amphiphilic.
Amphiphilic, amphipathic.
Mhm.
Amphoteric has a different meaning.
Yep, and it's kind of related to negative and positive, which is kind of the principle here. But it means it can act as both an acid and a base. Which means that if we're at acidic conditions under the dye selector point of the protein, our protein will, for the most part, have a positive charge on it, which then allows it to bind this Kumasi blue dye, which is a negatively charged dye. So that allows us to bind the proteins. And so based on, because it's in acidic conditions, that binding switches the color from red to blue, so that you can then measure the absorbance there again. So going back and forth between these two methods, some differences, for example. So these are both oftentimes what we would use, like if we're working with like solutions in the lab, and you want to see how much protein they are, or after centrifugation, things like that. How you decide which one, for example, if you need to add a reducing agent to solubilize your sample in this one, using the BCA method doesn't work super well because you just have added more reducing agent. So is your absorbance due to the reducing agent you added to solubilize the protein or the protein itself? Where using the Bradford, where it's dye binding, is working by a different method, you would be able to use that one instead, for example. So sometimes you have to figure out what you have based on what you have on hand, and then also slight differences in the principles of these methods to adapt to what you're going to use. So there's problems with like you need clear solutions because you're measuring absorbance, which can be really hard with proteins. And then sometimes you get problems, like for example with this one, is if you have very small peptides. So just to kind of recap a little bit before we go on and talk about UV. So we talked about Dumas and Kaldau, IR, and then under the research methods, we just talked about BCA and Bradford. You also, in the book, it talks about the Viret and Lowry methods, which are also methods that work based on the reducing capabilities. So similar to BCA. So there again, it's kind of like what you have in hand, what you make up, what you commonly buy. The last method we're going to talk about is UV. And so, as we talked about quite a bit on Monday, we can measure the absorbance at 280 nanometers. So what are we actually measuring the absorbance of? Kind of up there, but somebody remind me. What measures at 280 nanometers in the protein? Nope, not quite. So which one? Yeah, the aromatic amino acids. Here's Sam. So the peptide bonds are actually at 220, where the aromatic amino acids are the ones that are 280. We prefer absorbance at 280 because that's electronic we're looking at. So it's more sensitive than like the vibrational of the peptide bonds at 220. The challenge though is specifically it is your tyrosine and your tryptophan and tyrosine that have the higher molar extension coefficients of absorbance at 280. But if you have small peptides, you might not have those amino acids present, which means if you're doing things like, for example, HPLC, with like caffeine as your detector, you could use UV as your detector, but if you have small peptides, you're not going to see them because if they don't have the aromatic amino acids. And I was actually just doing some reading myself for my project, and that can be a problem with like some of the casein proteins, for example. Might not have a lot of aromatic amino acids. How we do this though, to measure the concentration, you can do it two ways. You can either use Beers-Lambert law, or you can create a standard curve again. What's nice about it is non-destructive and rapid. So like I said, for example, with one of my projects right now, I separated a protein into different fractions using that HPLC where I got multiple peaks I would pull up. I was able to detect them non-destructively so that I could collect them and use them for other research, which is really commonly done. Any questions on that? Or on any of the research methods I just went over? So in lab next week, you guys are going to see how to do Dumas, Kaldau, and Bradford. So you're going to get a nice little variety. And that's what I have for you guys. Thank you. I mean, I could.
Thanks, Chelsea. Okay, I'm back. Why are you sad that I'm back? Thank you. Deserve a chocolate for that. Just come get it when you're gone. Where are we? Oh, there. All right, continuing with proximate. Moving on. So far we did moisture, ash, fat, protein, now fat. You already did fat in the lab, so you already kind of are pros. This is going to be a refresher with some basic information. So I expect a lot of participation and a lot of candy flying around in the room. Okay. So the term lipid, or what? Okay, the following is true. The term lipid can be used for both oil and fat. Oil has higher melting point than fat. Fat has less saturated fatty acid as compared to oil. Some basic information from food chem, and this information actually will be helpful when we cover the fat characterization lecture later on in the lab. So, Laura. A is true. Anybody is going to counter Laura? Oops, sorry. Nobody's going to counter Laura. She is correct. Fat has a higher melting point than oil. That's why fat is present as is solid at room temperature. And then fat has less saturated fatty acid. No, actually oil has more polyunsaturated fatty acids and less saturated fat has less saturated fatty acid as compared to oil. Hold on a second. It's false. Yeah, it's the other way around. I thought I was asking what is false. Got confused myself. Okay, so no. But yes, the term lipid is often used for both oils and fats. Okay. So the lipid portion of food can include vitamin A and D, consists of fractions with varying polarity, cannot be completely extracted using ethyl ether. Again, a combination from what you know from food chem. This won't fly very good, so I want to see where it falls. Okay. Skittles. Even the wrong answer will get you a Skittle. Oh. Heads down, heads down. Almost. That is correct. So vitamins, actually the fat-soluble vitamins A, D, E, and K are within the lipid portion of the food, just because they're soluble in the same kind of solvent as the one that we solubilize the fats and oils. So they are under the lipid compartment or portion of food. They are considered there. And yes, we do have varying polarity. So we take triglycerides, the most hydrophobic, and then we have, yes? Yes, it is. What did I say? That will be all of the above. No, nothing. There's not one solvent that would extract all types of fat. It is. Ethyl ether is more diverse than PET ether. PET ether is more classified towards hydrophobic. Ethyl ether will do a better job at extracting more types of lipid, but not for completely. There is not one solvent that will completely extract everything. So I was wrong by saying that A and B is correct. All of the above is correct. And that was Sammy's. It is no. You don't say no. Why don't you want chocolate? That's okay. Don't pass the chocolate. Okay. What's the definition of lipid? Cece. Huh?
Something that's not dissolving water, it's not dissolving organic solvent.
Thank you so much. This is the absolute correct answer. There is no specific definition for lipid. It's specified lipid, anything that is not soluble or purely soluble in water. So whatever is soluble in organic solvent would be classified as lipid in a food matrix. Okay, so lipids can be simple lipids, such as esters of fatty acids, so triglycerides. So where you have 3 fatty acids esterified to a glycerol. So once it happens, it's a condensation reaction. So you have 3 fatty acids with a glycerol. So the OH from each of the fatty acid and H from all of the hydroxyl groups of glycerol will be removed as H2O. So 3 molecules of water will be removed when you have fatty acid, 3 fatty acid, and glycerol. So keep that information in mind when we cover fatty acid, fat characterization chapter. So lipids, we have triglycerides, we have di and monoglycerides, where it's actually produced to be emulsifiers, so they can hydrolyze off 1 fatty acid or 2 fatty acids. So you would either have a monoglyceride or a diglyceride, and they're excellent emulsifiers because they are slightly more polar. So mono and diglycerides are slightly more polar than triglycerides. Other esters of fatty acids, so vitamin A, for example, it's an ester with palmitate, which is a palmitic acid or one of the fatty acids, and then the alcohol is retinol. So instead of glycerol, you have retinol. And then other compounds that are the conjugated lipids, so phospholipids. So when you have a phosphate groups and 2 fatty acids, so that is a phospholipid. Or lipoprotein, so protein and lipid or fatty acid combined, lipoprotein, carbohydrate, moiety and lipid, cerebrosides, carbohydrate, nitrogenous compounds, and fatty acid. So these are compound lipids, we call them. Derived lipids, so when you have hydrolysis of lipids, for example, you end up having 3 fatty acids, and then long-chain alcohols, hydrocarbons, fat-soluble vitamins. So these are derived lipids. Yeah?
Does a retinol act differently than a glyceride?
No, it does not act. It's just a different molecular structure, but it is still an alcohol. Why is it important to analyze fat content? We always ask this question. We're doing this analysis. Why do we care? What's the first thing that would come to mind? Health claims. Okay, so low fats, skim milk, 2% milk. What else?
Nutrition labeling.
Oh, nutrition labeling. Yes. What else? Who is sitting very far away and deserves a bubble gum at this point? Sammy got it. She doesn't want it. Give it back. Okay, so what else? Amanda? Yes, excellent. Shelf life. So the fat content is directly related to the stability and hydrolytic or oxidative sensitivity over time. That is very good. I don't know if I had anything else. Oh, well, there's one more, very important. You back?
I am.
Yes.
Is it standard of identity?
Standard of identity, yes. Standard of identity, so some products have standard of identity like cheese or milk, for example. So you have to have certain percentage of fat, and then some products don't necessarily have standard of identity, but you have certain manufacturer specification. Yeah, I think we addressed all of that. Okay, now that you are experts in fats and why they need to be analyzed, let's look at methods. So we have so many different methods that we can use for analysis of fat. So we have the solvent extraction methods. There's the continuous method, which we didn't have in the lab, but I will talk about it briefly. It's one of the old methods for fat extraction. Semi-continuous, which you did in the lab, and discontinuous, you also did in the lab. And then two other methods. One is with still a solvent method, and it is with using solvent under elevated pressure and temperature, supercritical fluid extraction, and accelerated solvent extraction method. We'll talk briefly about those later. And then the GC method, which involves extraction first of the fat, if you're not working directly with oils or oil or fat, pure fat or oil. If you have a sample that you need to determine the fatty acid composition, for example, you would need to extract the fat first. And anyway, the fat on the label is actually generated using GC method. So you would have to extract the fat, and after you extract the fat, you would subject it to the method that you actually did for the GC lab, where you saponified your oil, broke down your fatty acids, freed them from the glycerol, and then esterified them with methanol. So you got them fatty. I'm so tired. Fatty acid methyl ester. Okay. At least I didn't start talking in a different language. That means I'm super tired if you hear words that you don't understand. Okay. So the other two methods that we'll talk about is these are methods that are not based on solvent extraction. So we call them non-solvent wet extraction methods. They're mostly used for dairy, but we're going to talk about them. There are also the instrument methods, so IR, mid-IR, and near-IR, but these are secondary methods of analysis, so they require calibration. And then there is also the Fosley method based on density and NMR. Okay, so we'll start off first, before diving into the different methods, sample preparation and solvent selection. So sample preparation is, some samples require preparation for certain types of methods. So depending on the type of food, so if we have high carbohydrate food or high protein food or high moisture food, so they require certain preparation, and then I'll talk about it a little bit more. Nature of lipids, do we have more of the hydrophobic type of lipids? Do we have a mixture of polar and non-polar? Or what type of extraction method we are using? If we're using Soxhlet, we need to dry the samples, for example, to less than 10% moisture. If we're using Muginer, we don't need to dry the sample because you have this mixing, you do vortexing, you shake. So with the Soxhlet, you don't have that mixing capability. So then your solvent will be hindered if you have a lot of moisture in your sample. So, like I said, sometimes you need to pre-dry. When do you need to do acid hydrolysis? You've done the labs already. Anna? That was with the cheese samples. Did we do acid hydrolysis with the cheese samples? When do we need to do acid hydrolysis? For what types of food mostly? Well, yes, you can do that, but mostly foods that are high in carbohydrates. Okay? Yeah, high in protein too. When you hydrolyze with HCl, you basically break the matrices that might interfere with the solvent reaching the fat. So if you have a complex matrix that's high in carbohydrate, for example, and protein, the lipids are usually entangled in this matrix. So when you hydrolyze with HCl, you break down that matrix and allow the solvent to reach to the lipid compartment and pull it, solubilize it. Of course, we need particle size reduction because you want to enhance the surface area so that you have more efficient extraction. So here's a table that demonstrates that with acid hydrolysis, you get better extraction of fat. So dried egg is high in protein, right? So yes, acid hydrolysis helps out. So no acid hydrolysis, you have about 6% less fat extracted. And with noodles, for example, they're low fat, but without acid hydrolysis, you get even lower values for fat. So basically, it helps when you have high carbohydrate, mostly high protein, low fat. This will help extract the fat better. So solvent selection.
I don't think I understood the table.
Oh, the table. So we're doing an analysis of fat, and this is with prior acid hydrolysis, prior to extracting the fat, and this is without acid hydrolysis. So with acid hydrolysis, you have higher percent of fat measured than without acid hydrolysis. So this is illustrating that breaking down the matrix helps with extraction of the fat and better estimation of the fat content. So with solvent selection, in order to extract, we look for solvents that have zero or low solvent power for proteins and carbohydrates. You do not want to solubilize any proteins and carbohydrates. Low boiling point so that you have your evaporation is more quicker, readily, evaporate readily, non-flammable, non-toxic, non-hygroscopic, that means they do not get saturated with moisture or that they not absorb moisture, and inexpensive. Now, is there a solvent with all these characteristics? There is not. The most common solvents, there are many that are used in fat extraction, not listed here, like chloroform and hexane that are used for fat extraction, but these are the most common ones. So ethyl ether is generally better solvent for fat. So it solubilizes hydrophobic and hydrophilic, but again, like I said, there is not one solvent that extracts everything. And petroleum ether is selective for more hydrophobic lipids. That means if you have high levels of phospholipids, for example, they won't be extracted with petroleum ether. Ethyl ether is more expensive than petroleum ether. That's why for Soxhlet that we need 350 milliliter per sample, we tend to use petroleum ether, especially if it's teaching now. So we tend to use the less expensive solvent. Ethyl ether can be saturated with moisture, whereas petroleum ether not as much. So if you have hygroscopic, if you have high moisture food, that can get problematic when you're using ethyl ether. It can get saturated with moisture, it can hinder the solubilization of fat. One is more flammable than the other, and they both have very low boiling point, 34 to 38 degrees C. So what's the solution? Use them in combination. If we use them in combination, we can extract, in general, most of the lipids, and we can get kind of like somewhere in between and expensive to cheap. And we kind of get the hygroscopic and less hygroscopic quality kind of in the middle. So that's why in Mujiner we use both ethyl ether and petroleum ether so that we can get the benefits of both together. Goldfish apparatus, this is an old type of unit. Actually, when I was a student, I used that for fat extraction. I didn't have Soxhlet. Actually, I never saw Soxhlet until coming here to the U. Even when I taught somewhere else, I used goldfish apparatus. So, let me state a little bit what happens with goldfish apparatus. It's a continuous method for extracting fat. So, same principle as the the Soxhlet you've seen in the lab already. So there's hot plate, there's a condenser, and then there's where you put your sample and a beaker for the solvent. To see it more closely, so you have your thimble, so you use the same thimble that you've used in the lab, and it is porous, so allow the solvent to go through. So you weigh your sample in, you put your glass wool material, and then you put it in a glass kind of tube, but it's open from here. And that you hook up to the condenser. So that's your condenser with water circulating. And then you have a beaker that you put your solvent in. So that's the setup. So, and then there is, you screw this whole thing onto the condenser, and then you have your hot plate here. So same principle as with the Soxhlet. So you heat, the solvent evaporates, and then it condenses down into the sample, and then the fat gets solubilized and then gets into the solvent. So you will end up here having solvent plus oil or fat in here. So it's continuous. So there is no soaking step. In Soxhlet, there is a soaking step. Here, you don't have a soaking step. So it just goes up, condenses down, and back up again. So there is a chance of channeling. Channeling meaning that the sample, the solvent goes up and down through the sample without carrying any fat with it, without solubilizing the fat. Okay? So that is one which makes it less efficient than having a soaking step with the Soxhlet in there. And another problem with this, which happened to me as I was teaching somewhere else. So see this here? So that's where you screw this on. And if you don't screw it on very tightly, guess what's going to happen? No, it will hold. Something more terrible will happen. Leaking. So if this is not closed up well, the solvent is going to go up and then leak, and guess where it's going to get on? The hot plate, and guess what can happen? What? Fire. So I was teaching one time, the students behind me, and I was explaining, and I look around, it was leaking. Before I could react, it blew in my face. So burned my eyelashes, my hair, but I survived with no scars. The students were safe because I was blocking it all. I took it all myself. See the sacrifices teachers do? Okay. Soxhlet, you all seen Soxhlet already. So for those of you that weren't in the lab, I'm not talking about names. Okay, so it's the same setup. So you have a hot plate here. You put your thimble in this compartment right here, and then you have a condenser with water. So your sample is now in the thimble. Your solvent is going to boil, evaporate, goes through this larger tube here and up into the condenser and condenses down into your sample. And then there will be a buildup of solvent with your inside that chamber where your thimble is. So there's that soaking step. And that's why it's semi-continuous, because there is a period of time where the sample is just soaked with the solvent. And then once it reaches a certain height, another little tube gets filled up to a certain point until a certain pressure is built, and then it siphons back. That means that whole solvent will drip back through that little tube back into this compartment, carrying the fat with it. Now you think this is safe, right? Okay, well, first year I taught this class, I didn't know anything about Soxhlet. It looked safer than goldfish for me. So we set it up not under the hood. Don't ever do that. So we set it up not under the hood, and then my TA at the time cranked up the hot plate all too high. We put out the sample, and guess what happened? So instead of going up and condensing down into the thimble, it started coming out from the other end. Then all the solvents started coming out from the top onto where? The hot plate. So like, oh my gosh, it's happening again. I told the student, don't panic, get out of the lab. And they were not panicking. I was the one panicking. Because it happened to me before. So, but nothing happened. We turned off the hot plates. And after that experience, it's under the hood. And we turned the hot plate. Actually, I tell Cindy, please don't turn the hot plates on until I put the samples on. So we don't turn the hot plates on. And when we put the sample, we turn it on and to a low heat, not high. We don't crank it up high. Okay, so one last thing, we have a minute. Both are gravimetric method, that means we weigh the sample. We take measurements before the fat extraction and after fat extraction. If we're doing cheese, for example, the percent fat would be on dry basis. So you can weigh the flask before you add the solvent and after you evaporate the solvent, and then you get the fat. Or we measure the whole thing like we did in the lab, before and after fat extraction, and the difference in that would be the fat content. We get the percent, and then we get the percent fat. So we'll start with this next time. We'll do that in class on Friday.
Yeah. In my opinion, that's